Welcome back to the course on computer network and internet protocol. So today we are going to cover the last topic of internet quality of service. So we are going to talk about two specific quality of service architectures called integrated service architecture or INSERV architecture or the differentiated service architecture or DiffServ architecture. So in the beginning, let me give you a brief idea about the differences between this INSERV and the DiffServ architectures. We have two modes of services to provide quality of service over the internet. So, the first mode of services which we call as the guaranteed service, that is the integrated service architecture. So, the integrated service architecture, what we try to do, we try to provide a kind of guaranteed service to the end users based on their service level agreement. So, what is mean by guaranteed service? Guaranteed service means if the service level agreement says that all of my packets should not get more delay than 10 millisecond, then the network will ensure that all the packets of mine which are coming from my devices, they will get less than 30 millisecond of delay or the 10 millisecond of delay that I have on my service level agreement. That we call as the guaranteed service. Now, you see that for this kind of guaranteed service to support this kind of integrated service architecture, what you need to do? You need to ensure that every individual router in the network should take care of about your service level agreement. So, every individual router need to make an estimate whether it will be able to provide your service or they need to do a pre-reservation of resources inside the routers to ensure that the specific service level agreement is met. Now, to do that, the routers need to coordinate with each other, because the packet is flowing through multiple routers whenever it is moving from one source to another destination, and then individual routers need to coordinate with each other to reserve the resources for you such that it can guarantee the service that is promised to you. So, this particular architecture we call it as integrated service architecture. Now, in this integrated service architecture, the problem is that this coordination among the routers. Now, if you think of the scale of the internet, you have millions of routers, and whenever you are transferring certain application, then it need to pass a large number of routers. They are under the control of different service providers at different levels. You have this tier 0 ISPs, tier 1 ISPs, then tier 2 ISPs, then the local ISPs. So, all these different service providers, they need to coordinate with each other, and the entire mechanism is very much complicated for this internet scale or internet level implementation. So, that is why we have a second class of quality of service which does not give you guaranteed quality of service, or which does not ensure that whatever the network service provider has promised to me in terms of service level agreement, for 100% times that will get executed, but what it tries to do? It tries its best to meet the service requirements. So, it is like that if your network is too congested, you cannot do anything. In that case, your packets will suffer, but if the network has a medium load, then it will provide you the required quality of service. Again, the scenario come from the example of airport that security check scenario, that if your airport is very much loaded with millions of passengers at the peak time, then the security guards also cannot do anything. So, what if you do you transfer some passengers from one queue to another queue, it does not matter much. But whenever the load is high, but not very high, during that time the security officials, they tries to provide certain quality of service. They finds out that well, certain queue is growing longer, but in other queue there are remaining passengers. So, they shift certain passengers from one queue to another queue, and they tries to provide you some level of quality of service based on the best that they can do. So, this kind of architecture we call it as a differentiated service architecture or DiffServ architecture. So, for internet scale implementation, DiffServ architecture is more suitable, where you just try your best to provide the quality of service, but there is no guarantee that 100% of the time it will meet the desired quality of service. So, we will look into this IntServ architecture and the DiffServ architecture in details. So, first start our journey with this integrated service architecture. To start with, first let us look the service architecture principles in the internet. We call it the Internet Service Architecture or ISA. This Internet Service Architecture or ISA, it provides integrated service QoS architecture over the internet. So, it has few steps like the admission control. So, this admission control for quality of service, you require reservation for the new flows. For that we run something called the resource reservation protocol or RSVP. We will look into this RSVP in little more details. Then you have the routing control. So, you make the routing decision based on the quality of service parameters. So, you find out that whether a particular router is loaded. If a particular router is loaded, then you rather not route the packet to that router, rather you route it to some alternate router. So, your routing algorithm is also depending on the depends on the quality of service parameters. Then have the different kind of queuing strategies that we have already discussed in the last lecture, which takes account of different flow requirements. And finally, you have discard policy like the congestion avoidance algorithm to meet the required quality of service, like the random early detection algorithm that we have discussed earlier. So, this is this entire ISA architecture of ISA architecture that runs inside a router. So, if you look into this ISA architecture, you have these routing protocols which are finding out the routing paths, and then you have the routing database, and that is the routing part which is running inside your router operating system, and then you have this quality of service associated protocol. So, this quality of service associated protocols, it has this admission control part, it has this admission control protocol, it ensures that the packet which we are going inside the network, they meets the required quality of service. So, for example, whenever you are admitting a new flow in the network, then you need to ensure that the new flow gets service from the internet, or that it gets the required service from the internet. If you do not able to ensure that the required flow get the required services from the internet, then you simply drop that particular flow. So, this particular thing possibly you have observed when making a voice call. Sometime you have heard that nice voice from a lady that all lines are busy, please dial after some time. So, it is just like the network is not allowing you to get admitted in the network because it does not have sufficient amount of resources. So, that is the purpose of this admission control protocol. Now, this admission control protocol get input from the reservation protocol. So, the reservation protocol actually reserves the resources in individual routers through the RSVP protocol that we will look after a couple of slides. So, this RSVP protocol or the resource reservation protocol, it ensures that the resources are getting reserved in individual routers in the end-to-end path. So, if you are not able to reserve any further resource, then the admission control will deny your entry to the network. Then you have a management agent which manages different functionalities of the quality of service, like this traffic shaping, traffic polishing and all these aspects. And then you have a traffic control database. So, this traffic control database actually tells you that how your packets need to be treated by the network. Now, let us come to the forwarding plane of the router. So, the forwarding plane, whenever you are getting a new packet, then first you have this classifier and the route selection. So, this classifier and the route selection mechanism, it will classify your packets into one of the available traffic classes, and then based on that it will select the route by looking into the routing database. Then comes your packet scheduler. So, this packet scheduler, it will get input from this route information as well as from the traffic control database, that how your packets need to be treated, and then it puts it in one of the queues. So, either in the best effort queuing, or you can have multiple queuing for the quality of service traffic. So, the QoS associated queuing. Then your scheduler is running, which actually runs on these queues and transfer the packets based on one of the queuing policies. So, that is this entire RSA implementation inside a router that actually integrates the routing and quality of service together and makes integrated treatment over the packets which are coming from the end user applications. Now, let us first look into the resource reservation protocol. So, this resource reservation protocol or RSVP is a network control protocol that allows data receiver to request a special end-to-end quality of service for its data flow. So, you require certain kind of special quality of service for your end-to-end flow. For that, you apply this resource reservation protocol. Remember that RSVP is a network control protocol and it is not a routing protocol. It works with IP, that is true, but it works in association with IP. So, if you look into the earlier slide, we have the routing control protocol here, which takes care of your routing, and then your reservation protocol, the RSVP is running here, that takes care of this resource reservation and individual routers. So, it is not a routing protocol, rather a QoS protocol which works in association with routing. Well, so it is designed to operate with current and future unicast and multicast routing protocols. So, this is the architecture for integrated service architecture and RSVP together. So, we have just shown the instances of two different machines, the host machine and the router machine. So, the first one is so this is the host machine, the module which runs inside the host machine, and these are the module which runs inside the router machine. Now, inside the host machine, let us see the modules that we have. So, you have the applications which are running there. That application talks with the classifier that classifies your packet, what type of quality of service classes that packets belongs to. And then you have a RSVP daemon. That RSVP daemon actually runs in the host as well as in all the intermediate routers. So, this RSVP daemons, so you can see that these RSVP daemons, they talk with each other. So, you have an arrow connecting the individual RSVP daemons. So, these RSVP daemons talk with each other and reserve the resources for a particular flow inside every routers in the end-to-end path. So, it finds out whether it is able to resource the reserve, it will able to reserve the resource for a particular flow. If it is able to reserve the resource, then it allows the flow through the admission control mechanism, otherwise it simply drops that particular flow. Now, you have that packet scheduler that works in cooperation with the classifier and the RSVP daemon that talks about that what type of resources have been reserved for you, and accordingly the packet scheduler schedule the packets into multiple queues. Now, again the similar thing happens here, that you have the routing protocol daemon which is running inside the routers. So, this routing protocol daemon in association with the RSVP daemon and the packet classifier, you decide the next hop which is coming from the routing part and your corresponding class queue which is coming from this RSVP part, RSVP and the classifier part. And then your packet scheduler will actually schedule your packet based on your next hop and the class queue that is being determined, and then the packet will be sent to the next router, and in every router this particular thing will run. So, remember this important aspect of this RSVP daemon at both the host and all the intermediate routers. So, all the RSVP daemons in all the routers in the end-to-end path, they need to coordinate with each other, and that is why implementing this integrated service architecture over the internet is a difficult thing, because you need a coordination among all the routers, which is difficult to achieve for a large scale internet. Well, let us look into certain RSVP terminologies. So, quality of service is implemented for a particular data flow by a mechanism that we call as a traffic control in RSVP. We have the packet classifier that determines the quality of service level, and the packet scheduler that link layer dependent mechanism to determine which particular packets are forwarded. Now, for each outgoing interface, the scheduler achieves the desired interface, desired quality of service. So, if you look into a router perspective, you can have multiple outgoing interfaces like ETH0, ETH1, ETH2, ETH3 and so on. So, these are the different outgoing interfaces for a router. Now, for every individual outgoing interface, I need to maintain these multiple queues, because you remember that these queues are specific to outgoing interface. So, with this outgoing interface possibly another router is connected. So, that is why for every interface you need to apply this queuing mechanism. So, the routing algorithm will tell you that in which outgoing interface the packet need to be forwarded to, and then in that particular outgoing interface you run the queuing mechanism to serve the packets to serve all the packets which need to be forwarded to that particular interface. Now, this is the reservation procedure for RSVP. During the reservation setup, first we send an RSVP QoS request, which is passed to two local decision module. The decision modules are the admission control module and the policy control module. Now, the admission control module, it determines whether the node has sufficient available resources to supply for the requested resources. If you have sufficient amount of resources, then you allow the flow to enter in the network, otherwise you simply drop the flow. Then you have the policy control module. This policy control module determines whether the user has administrative permission to make the reservation. Now, that is an important aspect in the internet scale. So, for example, you have not made the specific service level agreement. In that case, even if you are trying to send some voice over IP packet, that voice over IP packets will be treated as a best effort packet, not as an high priority packet. So, that is why you need to make the corresponding service level agreement with the network service provider before sending any quality of service associated packet. So, this policy control actually comes from the service level agreement that talks about whether the user is actually have sufficient administrative privilege to mark its packet as a high priority packet or not. Now, if this both checks succeed, then the parameters are set in the packet classifier and in the link layer interface to obtain the desired level of quality of service. If either of the check fails, like either your admission control check fails or the policy control check fails, then the RSVP program returns an error notification to the application process that generated that request, that you are not allowed to send this packet over the internet with this quality of service which you are claiming. Now, let us look into the reservation model in RSVP, how RSVP does the reservation. So, RSVP request, it consists of two parts. One thing we call as the flow spec and another thing we call as the filter spec. So, this pair is known as the flow descriptor. So, this flow spec, it specifies the desired level of quality of service. So, what type of quality of service you are expecting from the end user. And the filter spec together with the session specification defines the set of data packets, like this filter spec actually talks about that what type of queuing mechanism you want to implement on your packet. Whether you want to go for priority queuing or a custom queuing or a weighted fair queuing or whatever other queuing mechanisms that we have to provide internet quality of service. So, this flow spec, it is used to set the parameters in the packet scheduler, whereas the filter spec, it is used to set the parameter in the packet classifier. So, based on the filter spec, you actually filter out the packets, that is why the name filter spec. So, it is put in the packet classifier to classify the packets and then design that or put that packet associated with different type of queues that you have to provide quality of service. And the flow spec, it is used to set the parameters in the packet scheduler, that what would be the individual parameters to setting up the queues. Now, this flow spec, it is a reservation request, it generally includes a service class and two sets of numeric parameters, one is called the R spec, another one is called the T spec. So, this R spec defines the desired quality of service and the T spec defines the data flow, that which particular packets of a flow you are going to consider. So, here is a flow spec structure. So, you can see that it contains multiple parameters like this token rate, token bucket size, the peak bandwidth, latency. So, this token rate, token bucket size, they are kind of belongs to the RSpec that talks about the scheduler parameters, whereas this peak bandwidth, latency, delay variation, all these things they talk about flow specific parameters, the maximum SDU size, minimum polish size. So, they belongs to the T spec of this flow spec. So, this flow spec specifies all these numeric values which actually determines your corresponding service level agreement. So, based on the flow spec you determine that what level of quality of service you want to provide to a particular user, then you control or you configure the intermediate routing queues based on these particular parameters. Whereas, in case of filter spec, you are actually marking the packet classifier or you are configuring the packet classifier to say that well this particular user may generate VoIP traffic, video on demand traffic and the best effort traffic as per its service level agreement that the traffic classifier needs to take care of. Okay. So, the problems which are associated with RSVP, there are major two problems that I have already pointed out, that the RSVP daemon needs to maintain power flow states at intermediate routers, because the RSVP daemon needs to maintain power flow states at intermediate routers. It is a heavy process. So, use of this power flow state and power flow processing, it raises the scalability concerns over a large network. And that is why from the integrated service architecture we move towards the differentiated service architecture or DiffServ architecture. So, this differentiated service architecture or the DiffServ architecture, it is a coarse grained class based mechanism for traffic management. It has a packet classifier which uses a 6-bit differentiated service code point field or the DSCP field. So, this DSCP field which indicates that in which particular traffic class it belongs to. So, remember in case of your integrated service architecture, the packet classifier or the classifier classes are not fixed or predetermined. It can be user based or it can vary from user to user, and that is why we are using filter spec to inform the classifier that what different type of packet classes can belong to a particular user. But in case of differentiated service architecture, we do not have that level of flexibility. We do not have this kind of user specific quality of services, that rather network wide we have some fixed classes of services, and those fixed classes of services are determined by this DSCP field. So, DSCP field is included inside the 8-bit differentiated service field, the DS field inside the IP header. So, in the IP header itself we will find out this DS field which contains the DSCP field, and that DSCP field determines the fixed traffic classes that the differentiated service architecture can support. So, that is the difference, a major difference between the integrated service architecture and the differentiated service architecture. And that is why this kind of filter spec model it is not required in case of DiffServ architecture, because your traffic classes are fixed, and that is why your classifier has a fixed behavior rather than a user specific behavior. In case of your integrated service architecture, you had this user specific behavior, and that is why you had the requirement of the filter spec to configure the traffic classifier. Now, DiffServ routers implement something called the power hop behavior. So, this power hop behavior defines the packet forwarding properties associated with a class of traffic. So, how the packets will be forwarded for DiffServ routers. Now, DiffServ recommends standardized set of traffic classes that I have mentioned. It has standardized and fixed set of traffic classes. Now, a group of routers that implement a common administratively defined DiffServ policies, they are referred to a DiffServ domain. So, we will implement differentiated service architecture over a DiffServ domain. Now, this is the architecture of DiffServ. You have multiple DiffServ domains, DiffServ 1 domain, DiffServ domain 1, DiffServ domain 2 and DiffServ domain 3. Now, whenever you are transferring a packet from a source to a destination, it need to go through these 3 DiffServ domains. Now, when it needs to go through these 3 DiffServ domain, what we do that we look into these intermediate routers at the edge routers. So, the idea of this differentiated service architecture is something like this, that whenever you are entering a packet to one DiffServ domain, what you try to do, you try to make an estimation about what is the end-to-end quality of service requirement and how much quality of service it has already obtained. Now, remember this individual DiffServ domains can be like different service providers which are there in the internet. Whenever, so it may happen that this is a local ISP, this is say a tier 1 ISP, and this is again a local ISP. Now, whenever the packet is going through this tier 1 ISP, that this DiffServ domain actually looks into that what is my end-to-end service level agreement and how much service the packet from this source has already received. So, for at this point say my end-to-end delay need to be 30 millisecond, that is written inside the service level agreement, and what we see here that when the packet reaches here, it has already received 20 millisecond of delay from this source to DS1. That means from this DS2 to DS3 and final destination, you have to transfer the packet within 10 millisecond to meet the required service level agreement. Now, based on this differentiated service architecture actually takes the decision about how to treat the packet for this particular flow. To do this, it actually have a coordination among other DiffServ domain. Remember that unlike other integrated service architecture things that we have done, we require a coordination among all the routers. Here we do not require a coordination among all the routers, we just require a coordination among all the DiffServ domains, and that is done by this bandwidth broker. Okay. So, the bandwidth broker is an agent that has some knowledge of an organization's priorities and policies and allocates quality of service resources with respect to those policies as per the definition of bandwidth broker given in RFC 263. Now, in order to achieve an end-to-end allocation of resources across separate domains, the bandwidth broker managing a domain will have to communicate with its adjacent peers. So, here in the earlier picture, this bandwidth broker running at DS2, it need to communicate with the bandwidth broker at DS1 and the bandwidth broker at DS3 to determine that what level of quality of service can be given to a particular flow. Have to communicate with its adjacent peers, which allows end-to-end services to be constructed out of purely bilateral agreement. So, remember that it is a kind of pure bilateral agreement. So, you can, and why we call it as a best effort service and not a guaranteed service, again coming back to the previous picture, that it may happen that this particular service domain or this particular local ISP, it does not have a peering relationship with this tier 1 ISP. So, it does not have any agreement with DS2 in terms of this quality of service. In that case, it will not be able to provide that end-to-end quality of service. So, now we are giving the flexibility at the ISP levels that individual ISPs can ensure the peering with the or quality of service associated peering with the neighbors and can take the decision accordingly. That is the task of the bandwidth broker, which sets up this kind of peering relationships. So, the service level agreement. So, we have two type of agreement in DiffServ architecture. One is called the service level agreement, which is a set of parameters and their values which together define the service order to a traffic stream by a DS domain. And the traffic conditioning agreement is a set of parameters and their values which together specify a set of classifier rules and traffic profile. So, this traffic condition agreement actually is an agreement which says you that see I have this fixed set of classes and your packet will belong to one of these fixed set of classes. So, tell me that in which fixed set of classes you want to purchase. So, if you say that I want to purchase class 1, you have to pay more money. If you say that I want to purchase class 2 service, you have to pay little less money and so on. So, that we call as the traffic conditioning agreement. And the service conditioning agreement or the service level agreement is that well I am purchasing that class 1. My traffic is in class 1, but in class 1 traffic you should give little more priority to my traffic because I am going to use say VoIP services. So, it is just like multi-class of VoIP services. One is ensuring a perfect QoS, another one is ensuring some compromised QoS. Now, in a DS domain, the boundary nodes or the border nodes, they interconnect the current DS domain to other DS domain or non-capable DS domains. We call them as the boundary nodes or the edge nodes. Now, the classification and conditioning process of a boundary node in a DS domain, it is responsible for mapping packets to a forwarding class supported in the network and ensuring that the traffic from a customer conforms to their service level agreement. So, that are done by the classification and the conditioning process which is running in a boundary node. Now, the traffic conditioning, it is a set of control functions that is applied to a classified packet stream in order to enforce traffic conditioning agreements like how your packet need to be treated, which are made between the customers and the service providers. So, it has 4 components: meter, marker, shaper and dropper. Now, a meter is used to measure the classified traffic stream against the traffic profile. That means you need a meter is basically used to estimate that how much quality of service you have already got and what is the level of quality of service that you have to give whenever you are going to the next DS domain. And the state of the meter may then be used to enable a marking, that means classifying your packet in one of the service classes, shaping or dropping the action. So, here is the idea. So, you have a classifier, from that classifier it is coming to the marker. Now, the marker make an estimate, say your packet is say from the source, it is going to one DS domain, then another DS domain, then the third DS domain and finally, the destination. Now, when the packet is reaching to say this boundary node, say B1, it runs its meter, this meter module to find out that if you have a end-to-end 30 millisecond of delay requirement, what is the amount of delay the packet has already achieved. Say the packet has already achieved 10 millisecond delay. Now, it needs to find out that the packet has already achieved 10 millisecond of delay. So, I have to transfer the packet within 20 millisecond. Now, let us look into this packet status in compared to other packets which are already in my interface queue. If you can find out that the other packets need to be transferred within say average delay of 30 millisecond, but this packet need to be transferred within 20 millisecond, then you increase the priority of that packet. But if you see that the other packets need to be transferred in 5 millisecond and this packet need to be transferred into 20 millisecond, then you reduce its priority. So, that way the priority is dynamically assigned by the marker and that priority assignment is done by this marker module. And accordingly, you include the traffic shaper or dropper which will shape your traffic or drop your traffic or apply certain kind of scheduling policy to ensure the quality of service requirements. So, this classification and marking, they are the part of behaviors. So, we have 4 different type of part of behaviors. The default part of behaviors is to provide best effort service, the expedited forwarding or EFPHB to which is to give priority to the low loss, low latency traffic. Assured forwarding part of behavior, it gives assuring to delivery under prescribed condition, like you require some fixed amount of bandwidth for that particular application, then you go for assured forwarding, which can be implemented with the help of a custom queuing. The expedited forwarding on the other hand can be implemented inside a priority queue. So, you can apply a priority queue for this and a custom queue for this. And you can have certain class space selector part of behavior which maintains backward compatibility with the IP precedence field. So, something like you can use weighted fair queuing to ensure the fairness. Okay, these are the working steps of a DS domain. The source or the users, it make a contract with the ISP for a specific service level agreement. The source sends the request message to the first hop router, then the first hop router sends the request to the bandwidth broker, which send back either a accept or reject based on whether the bandwidth can be, whether the SLA can be ensured in delivering the packet. If it is accepted, then either the source or the first hop router will mark the DSCP field and start sending the packet. And edge routers, they at every DS domain, they check compliance with the SLA and does the policing. The excess packets are either discarded or marked as low priority to comply with the SLA, because the excess packets are marked as low priority. That is why you say it is not a guaranteed QoS, rather a expected QoS or the best effort QoS. Now, the code router, it will just look at to the DSCP and decides the corresponding part of behavior. Now, here are certain links that you can look further to understand in details the differentiated service and the integrated service architecture. So, these two topics are little advanced topic which are not there in your reference book that we have mentioned earlier. So, that is why we have given 2 links. So, you can browse through these 2 links to find out the details. So, this is all about the quality of service in the internet, and I hope that by this time you have a nice idea about what quality of service means and how to apply quality of service over the internet. You can go through this Cisco documentation that I have shared to understand more about this quality of service and how different types of quality of service are actually implemented inside Cisco routers. Indeed, the process is a bit complex, and there are multiple modules which work all together to support this. So, I tried to give you a very brief overview or a bird's eye view of this entire quality of service to give you an understanding about this topic. So, thank you all for attending this class.